No, I mean, that was stated what was. We called the second person came to fix it. Yeah, sure.
And the tech should have just fucking stayed here. I was gonna started talking. What? How do I watch this? How do I watch it? Oh, okay.
Thank you everyone for coming. So the title of my talk is Towards an Accurate Description of Strongly Correlated Chemical Systems with Stable Stability of Compound Cells. I realize that's a lot of big words and my main ultimate talk, which is a method using imaginary time and specific fields actually yields real and accurate predictions about chemical systems. Here's an outline of the talk. First I'll introduce a few target applications. Then I'll get to take the electron structure theory, which I'll explain, and yield some useful insights about the system. Then I'll sort of take a research and introduce the perspective of quantum chemistry. Try to get to the feeling of the way that quantum chemists affect all chemistry. Then I'll define what it means for electrons to be strongly correlated. And then I'll focus on three main types of systems in which these have a strong correlation. And those are temperature levels, stable biological, and non-stable. And then I'll introduce the optical application. I will examine each three-dimensional optical vector and compare them with how the chemistry lies out of the vector. And then I'll explain the unit. So the first target application involves transition metals in biology and catalysis. So here's an example. We have the iron sulfur clusters, which are in the active site of a protein called nitrogenase. They're also redox active in something called the electron transport chain, which in the end makes energy in the body. Here we have the oxygen evolving complex, which is in the active site of photosystem 2. And so plants use this cluster to split water into hydrogen and oxygen. So there are various unknowns about these types of systems. For example, what are the redox properties? That's another way of saying electron transfer properties. For this metal cluster, what are the spin and protonation states? Also, how exactly does water approach and get split into hydrogen and oxygen? That's a very useful reaction for synthetic catalysis. And so I guess very frequently, for these types of systems with transition metals, the available experiments are limited and often noisy. So I really think that experiments can be supplemented with insights from computational methods to deepen our structural and mechanistic understanding. And hopefully that will facilitate the design of alternate synthetic catalysts. Okay, so the second target application involves metals in drug discovery. So here's a seemingly innocuous molecule called cisplatin. Well, if you're here for an undergrad thing, I think it's in a different room.
They should have put a sign or something.
This molecule is called cisplatin. It seems harmless, but it was FDA approved in 1978 as a chemotherapy drug. And so what it does is it binds specifically to guanine bases, and then it interferes with DNA replication. So it'd be nice to be able to understand the reaction pathways of how such drugs work. Also, I recently read a review by Robinson and coworkers in which it was estimated that almost half of all enzymes in the body require a metal ion to function. So this is just a schematic. We have a small drug-like molecule, which in order to inhibit some biological function, it first has to bind into its active site. And in this case, it has to, in order to do that, it has to coordinate this manganese atom. So this is one example of very many. I mean, we can't read these now, but this is a list of drug inhibitors and the metal ions that they have to coordinate in the various protein targets. So imagine if we could understand and predict how drug-like molecules like that can interact with these metals. I think that would be a huge benefit for drug design. So the third target application is called optical upconversion. And this is something that I've recently been introduced to over the past year.
So I'm not an expert, but here's just one way to explain it. So if you shine something called infrared radiation, so you can't see that. That's very long wavelength radiation. You shine that at some chemicals in the dark. If you have the right chemicals, you'll see visible light that's emitted. So let me explain how that works. First, I'll introduce two concepts. There's two states called singlet and triplet, which are important to understand. The singlet has two electrons. One is pointing down, and one's pointing up. The triplet has two electrons both pointing up. And the triplet in general is a longer-lived state. And also the excitation energy is generally lower. And theorists understand this due to something called exchange. But yeah, so optical upconversion has two components. One event occurs at the sensitizer, the other at the annihilator. At the sensitizer, you have a ground state singlet, and then it absorbs IR radiation, or some low energy light, like red light. And then you'll excite the electron to the singlet state. It will then undergo intersystem crossing to populate this triplet state. And then at the annihilator, two of these triplets will fuse to form this high energy state. And if it's just right, like high enough above this S1, it'll transfer over and then it'll emit a very high energy photon. So there's two examples of how this can be useful. The first concerns solar cells. Typically you have to shine in light of precisely the energy to get to the first excited state, or the band gap. But here you can actually harvest lower energy photons to make more efficient solar cells. And so the second thing has to do with the low penetration depth of visible light. So if you want visible light in the body to do either imaging or various photo redox catalysis, you can't just shine it into biological tissue. But IR light, infrared light, can penetrate into the body. It can then produce visible light inside the body to do whatever you want. And so how might theory play a role in this? One example is that if we just calculate this triplet energy, which by the way is very difficult to measure in most cases, and if we double that and we compare that to this S1, we can screen maybe hundreds of possible annihilators, for example, and hopefully to improve this system. So these are the types of molecules, the sensitizer annihilators. All right, so a brief interlude into quantum chemistry. So most chemists, I would say, when they try to predict the reactivity of a molecule, there's a certain intuition that I believe is derived from the periodic table and trends in the periodic table. Things such as like electronegativity, atomic size, whether something's an acid or a base. But for a quantum chemist, the world is different. So we see chemical reactivity and we predict it by solving the Schrodinger equation. So for a quantum chemist, you see a molecule which is a bunch of point charges. So they're charged particles with nuclei, which are the atoms, like platinum, at position capital R alpha. The nuclei have charges, Z alpha, and they have electrons. And once you know that, you can fully specify this Hamiltonian operator in the Schrodinger equation. So there are many terms in this Hamiltonian. There's the kinetic energy of the electrons of the nuclei. There's the electron-nuclear attraction term. There's also the electron-electron repulsion and the nuclear-nuclear repulsion. So that's a lot of stuff. But typically, chemists make an approximation called the Bohr-Oppenheimer approximation. And so this relies on the fact that atomic nuclei have masses that are much, much larger than the electrons. And so we can ignore this term in most cases and still predict correct things. Finally, according to this approximation, the wave function is separated into an electronic part and a nuclear part. And the electronic part just takes the nuclear coordinates, which are fixed, as a parameter. And so this term in the relevant electronic structure problem becomes a constant. So this is the simplified Hamiltonian that we're dealing with. Okay, so what does it mean to actually solve the Schrodinger equation? I feel like you hear that a lot, but here's precisely what it means. So a certain molecule will define H, and given that, you have to find something called a wave function and its corresponding eigenvalue, which is the energy, such that this equation holds. And so if you can do this for all n, you then know all the electronic properties about the system that your Hamiltonian describes. So for example, electronic spectra, charge densities, and the thermochemistry. So in this slide, I'd actually like to point out that if you only solve for n equals 0, so the ground state of some Hamiltonian, you can still make a lot of useful predictions about chemical reactions. So here's a typical reaction coordinate diagram. We have the products, or the reactions, we have the reactants over here, and then typically you have to put in some energy to get over a barrier, and then you'll produce products. So from the quantum chemical perspective, you take the reactants, you build a Hamiltonian, and then you solve it for E0. And you can do the same for the transition state and also the products. And so, for example, if you take EB minus EA, both in the ground state, you can get the barrier height, from which you can derive reaction rates. If you do the same thing for C and A, you can get various thermodynamic properties. For example, the pKa's, the equilibrium conformational energies, and various other things. And so this is very general. So it doesn't have to be something like this. You could think of a redox reaction. So if you have a molecule and you remove an electron, this happens in batteries a lot. You can compute the ionization potential and electron affinities by just having two separate Hamiltonians, solving for their ground state, and then taking the energy difference. So other things include bond dissociation energies, the gaps between lowest energy states of different spin multiplicities, and these redox properties. But one does not simply solve for many electrons regularly. So there is a difficulty, which is known as the exponential wall. And so this is actually a technical term, but it's a wall that I've encountered many times in my career, and I can take my word for it, it's really hard. So if you take some small atom and you do a calculation, it might take an hour. But then you add some functional group, which doesn't look too big, then it takes 10 hours, or even more than that. So the underlying reason is that the dimension of something called the Hilbert space, which I'll soon define, of an n-electron state, the Hilbert space of n-electron states, the dimension of that grows exponentially with the number of particles. So here, this is a ground state wave function, which we saw for from the last slide. And you can expand this in terms of any particle states. So in this state, it's you have n electrons. Electron 1 is occupying some orbital, phi 1. Electron n is occupying some orbital, phi n. And yet, so if a single particle can be in m possible states, the n particle system will have a wave function with m to the n terms, all of which have to be determined. So let's take a simple spin half example. So if you have a fermion, some electron, that can either be pointing up or down, there's two possibilities for this single particle state. But if you have n of them, then the total space that you get, the number of dimensions in the Schrodinger equation is 2 to the n. And so that doesn't sound too bad, but 2 to the 0 is 1, 2 to the 1 is 2. But 2 to the 20 is a million. So that's the wall that I'm talking about. All right, so how do we get around this wall? So in fact, the name of the game in all electronic structure theory, not all, but a lot of them, is basically asking this question. How do we get accurate predictions in polynomial time? So one way to do this, it's not an easy problem. This guy figured out a way to sidestep this exponential wall. He won a Nobel Prize in the next 10 years for a theory called density functional theory. So this is widely used in chemistry in every department around the world. And the really nice thing about this is that the density now replaces the wave function as a central quantity. And the density is a function of just 3 coordinates, right? X, Y, and Z. And so if that's the central quantity, you no longer have to worry about this exponentially growing thing. So in one type of DFT, called Cone-Sham DFT, the interacting n particle problem is decoupled into a system of n non-interacting particles in an effective potential. And the solution, this is the point I like to emphasize in this slide, so the solution of the Cone-Sham equations is a single electronic configuration. So instead of having this sum over many different electronic configurations, in DFT, you can only get one configuration. And so, now I can easily define what it means for a system to be strongly correlated. And that's when multiple electronic configurations contribute to the wave function. So these C's, which are the linear coefficients, can be very large for multiple configurations. And so this situation is encountered in singlet biradicals, in transition metals, and in bond breaking events. But I really want to make the point that all these things they have the same physics is responsible. And that's that there are many competing low-lying energy levels that are important in this wave function for all these things. So let's start with one. The biradicals, I realize actually in chemistry there's this term can mean many things. But I guess for this talk, and I guess most theorists think that it means you're talking about a system where the valence electrons can be well described by a model which has 2 electrons in 2 nearly degenerate or degenerate orbits. So you don't have to go very far to find an example of that. This is diatomic oxygen, just O2. So the ground state is a triplet. So the two spins are up. There's two nearby singlet excited states, the open shell one and the closed shell one. And you need at least two states to get quantitative predictions for these singlet states. And that's a very general thing. And so if you're using DFT, you only have access to one state, or you can only use one state. You're missing the other one entirely. And if you compute the gap between this state and this state, which is called the singlet triplet gap, that's about 14 kPa per mole in the air. So there's another method, which is very well known as the gold standard in quantum chemistry. It's called couple cluster theory. And so in this version, it has singles, doubles, and perturbative triplets. So basically, you take one electron configuration, and you apply this operator. So in this excites one electron, this excites two electrons. So if you Taylor expand that, you can see that this wave function is the sum of many configurations. So in that sense, it's better. But it's still based on a single reference. And so, just if you compute the singlet triplet gap using this theory for this O2 molecule, the error is about 7 kcal per mole. So that means there's some excitations that are missing, even in this method. And so this is a problem because conjugated molecules relevant to photocatalysis, they can exhibit substantial biradical character. As you can see by this arrow pushing argument. You have these two unpaired electrons. Okay, so how about transition nodes? So these are the atomic orbitals of these iron, cobalt, nickel, copper, and zinc. They're called 3D transition nodes. So there's 5 degenerate orbitals in the atoms. And there's many, many ways that you could populate them with electrons. And the presence of these many nearly degenerate orbitals enables a very rich chemical reactivity. For example, you can reduce some metal complex multiple times, and then you can oxidize it. And so that's kind of cool, but it makes ab initio calculations very hard. So here's just an example of one study from a couple years ago. They take 60 transition metal diatomics, and they compute the bond energy, basically the energy it takes to form a bond. And so for each one, they do 10 different DFT functionals, and then they run this gold standard couple cluster method, and also a multi-reference variable. And so DFT, it's all over the map for these systems. Even couple cluster, it has sometimes very large errors, approaching, looks like 17 kcal per mole. And the multi-reference variant doesn't help you. Okay, so the third thing, instance where we encounter strong correlation in chemistry, as I said, was bond break. And I'll show you how it's a similar thing. Actually, this is very closely related to biradix, at least breaking single bond. So consider H2. At the equilibrium bond length, you combine the two atomic orbitals and they form a bonding orbital and an anti-bonding orbital. And so you can doubly occupy that bonding orbital. And this is one electronic configuration that mostly dominates. So you can use a single reference theory and it does very well for things like this. And many molecules, in fact, and the success of DFT and other theories like that, it's because of this. Like many molecules you can describe with one configuration, but some you can't. So when you stretch the bond length, then it makes things a bit more difficult. So you have two atoms far away. There could be 2 electrons over here, or there could be 2 electrons over here. But you need 2 configurations to describe them. So here's a plot of the bond energy as a function of the stretching distance for BH, the diatomic. And so it's really hard to see here, but this curve is the exact answer using something called FCI. If you use one configuration with restricted orbitals, it doesn't bind properly, like there's still this error, and it doesn't get the dissociation limit properly. And then if you do subsequent perturbation theory, which is what NB2 is, or if you apply that cluster operator, all of these things don't get this long bond length limit correctly. So there's something, you can unrestrict orbitals. That's a technical term, but it means that the spin-up orbitals are allowed to be different than the spin-down ones. And that allows you to qualitatively, even quantitatively get this dissociation limit right, but it's at the expense of a spin contamination at the intermediate regions. And so this is for C2, the dimer. And it's making errors of about kcal per mole or about 20 kcal per mole versus FCI, or the exact number. Okay, so now that I've explained this to you, I think you can sort of sympathize with me. Or you can sort of understand how excited I was in my first year of grad school when I saw this plot. So this is the chromium dimer, which is one of the most notoriously difficult systems in quantum chemistry. If you try to draw a Lewis structure, it has a quintuple bond. And so these are, from Hartree-Fock to various multi-reference methods and unrestricted CCSTT. Even this gold standard, the equilibrium bond length that it predicts is way off. And then I saw that there's some method, AFQMC, auxiliary field quantum Monte Carlo. And these two variants seem to do very well in describing this very strongly correlated system. So before I say more, I have to explain what this theory is. And so this slide has a lot of equations, and I'm all going to do this. So here's the Hamiltonian. So recall I showed this before, but it was in a different notation. So here we're using something called second quantization, where we have fermionic creation operators and annihilation operators. But it's exactly the same Hamiltonian as before, it's just in a different representation, where the anti-symmetry is in the operators instead of the wave function. And so the strategy of this approach is you take some starting point, and you apply this operator. So this occurs in imaginary time. You take the Schrodinger equation, substitute t for it, and you solve it. You get something like this. And so I was recently talking with my friend Ian, and he was describing this to me as applying this operator in imaginary time is the same as cooling down the system. And so if you cool down a system, you'll get ground state properties, and that's exactly what's happening here. So that's the physical intuition behind this. So how do we do this on a computer? So in order to do this, we first use something called the Trotter decomposition. To split the one electron terms, which are these terms, and the two electron terms. And the reason we do this is because of some theorem called Thales's theorem. And it says that for a one-body operator, which we'll call B, and some electron configuration phi, if you apply e to the b to some Slater determinant, which I didn't define, but it's just some kind of wave function, then you just get another single determinant, single electron configuration out of it. All it does is rotate the orbitals. And this is very computationally easy. So I can apply this thing to a state just with a simple matrix multiplication. So computers are very good at that. So then the natural question is, what do we do with this two electron term? So it's always possible to decouple this into a sum of squares of one-body operators. You just have to take my word. And then we do this because I think in the 1940s, there's something called a Hubbard-Steiner transformation, which takes the exponential of a square of a one-body operator into an integral over exponential of a one-body operator. So you think about this, taking a step back, it's mapping an interacting system exactly onto a sum of non-interacting systems, each in an auxiliary field. So if you do this transformation to this thing, you're going to get a very, very highly multidimensional integral. So this x is not a number. This x is a vector of dimensions millions, easily. And so you don't want to create grids for each dimension and compute this operator on every point in every dimension. That would be, that's exponentially hard. So there's a very general way to evaluate multidimensional integrals. This happens to be an integral operator, but it's still the same strategy. It's called Monte Carlo. So you just take one dimension, choose some grid point, you sample it, and then you start averaging the value of this operator. And the more samples you make, you'll converge the operator, whatever you're trying to average, to some value, and then you can get statistics, like a mean value and a standard error. So that's actually one way to get around the exponential rule. So in this Monte Carlo representation, if we bring it back to quantum chemistry, we have a wave function, and it's a weighted sum of electron configurations. So just by this form, we can take into account strong correlations, since we have multiple electron configurations. And also a more subtle point, unlike the coupled cluster wave function, these electron configurations they're allowed to be non-orthogonal. And so that will enable a very efficient description of multi-reference properties. Okay, so in practice, how do we do this? So we have a bunch of walkers, which are the things that are used to sample this integral. Each walker samples a set of auxiliary fields, x, k, from this distribution under the integral, p of x. And then you create this b operator, which depends on x, k. And then you use that to propagate the walker, using this theorem with a matrix multiplication. But I mean, nothing is free. For a realistic Coulomb interaction, if you want to deal with real molecules, this V operator is purely imaginary. It's a complex number with an imaginary component. And so even if you apply this operator a bunch of times, it'll slowly rotate the orbitals in the complex plane. Like each walker will accumulate a phase. Hence the phase problem. And so if you don't do anything about it, you can keep track of this phase by computing something called the overlap of the walker orbitals with some trial function. And if you plot that in the complex plane, you see that it goes everywhere. And the reason that this is a problem is that the walker weights in the wave function are written as this ratio. And so if you hit the origin there, your denominator will be 0, and your weights will diverge, and then the things that you're trying to measure, they'll just have a bunch of numbers. Okay, so what do we do about this? This was first presented by Shee and Henry Krakauer in 2003. So basically, you can reformulate the walker weights into this as a function of something called local energy. And then you do two things. First, you take the real part of this at the end of every step. And then you keep track of the phases of the walkers, and if after one time step, it changes by more than 90 degrees, you just zero the weight of the walker. But the key point from all this math is that this approximation is exact when this trial wave function is exact. Because you can apply this operator to the left, and then you get a real number. Therefore, the weights are real, and they remain real. But in practice, we don't know what the true ground state is. But still, it opens the door for systematic improvability by using better and better trial wave functions. Okay, so a few points about the algorithm. The compute time scales with the fourth power of the system size, at least for the chemical systems that I've coded this theory for. So this may seem high, but it's not exponential. Also, the traditional alternatives, the second order perturbation theory scales as the fifth power. The CCSTT scales as the seventh power. And recently, a good friend of mine, Mario, we discovered this tensor factorization technique, which can reduce the scaling to subcortex for large systems. Okay, so, but still, even if you have a low scaling, because you have many walkers and you have to apply pretty complex operations to each walker, that gives you a large prefactor. So the calculation is still expensive. But together with my advisors, we realized two critical things. The first is that most quantities of interest are or can be derived from energy differences. Remember that reaction coordinate I showed you? All those observables really were differences in energies. And so we developed something called the correlated sampling approach. The second point is that the AFQMC algorithm can be implemented entirely with just matrix operations. And thanks to things like Bitcoin and the need to train machine learning algorithms, these GPUs are becoming quite cheap. And so we thought it would make a lot of sense to speed up this code. So first, a few words about correlated sampling. So here's, again, is the imaginary time propagator, which we apply to each walker. If you consider you have two systems, for example, some molecule, and then another molecule with one fewer electron, or a singlet state and a triplet state, you can use the same x's, and if they're the same molecule, everything else will be the same. And so you can use very few walkers, so it'll be very fast. And if this is a plot of the total energies. If you use the same random numbers, essentially, they'll make errors in the same direction. And they might even be large. When you take the difference, the resulting trajectory is much, much smoother. And so that reduces the errors at equivalent cost. So here's a real example. We compute the ionization energy of a potassium atom. So here it's plotted the ionization energy as a function of imaginary time. And the red is if we don't use correlated sampling. The blue is if we do. And these error bars represent the statistical error from the QMC simulation. And so we find that for these redox reactions, and also similar things like spin splittings or decarbonation energies, we get speedups of around 10 to 50 times in computer time. So there's another property of the correlated sampling algorithm which is essential in treating larger systems. And that's that the speedup increases with the system size versus the uncorrelated method. So here, one way to increase the system size is to just use more basis functions to describe the wave function. And that makes your problem bigger. And so going from a smaller basis this way in the legend, that moves the error up. But if you use correlated sampling, it becomes almost independent of the number of basic functions. The real way to make a system bigger is to just add more molecules. So, water, methanol, ethanol, the molecules are getting bigger. And the same phenomenon happens here. The uncorrelated version, the errors go up, but when you correlate the sampling, they're pretty much unaffected. And so here, just the final point is that this algorithm actually has allowed us to reach energy scales that are really, really tiny. And a lot of interesting physics happens at these small energy scales. For example, like superconductivity, there's many different competing phases that are separated by a very small amount of energy. So this is just a chemical example. There's a certain system called dipole bound atom. If you take a molecule that has a dipole moment, which is sort of like the difference in the plus and minus charge distribution, if it's bigger than 3 to pi, that dipole itself can bind electrons. So this is a non-covalent effect. And then you get an anion that's very diffuse. This electron is very loosely bound. And so the experimental binding energies are 10 to a couple hundred wave numbers. So that's very small. The other QMC method that's being used a lot these days is called diffusion Monte Carlo. At least our collaborators ran very, very long simulations with a lot of computer time. And they couldn't seem to push the errors lower than that. And so if your error bars are 70 or 45, you can't really make a prediction that's result is 10%. But with correlated sampling, our error bars could get that low. And so we can make useful, significant predictions. Okay, so a few slides about the GPUs. GPU stands for graphical processing unit. Evan's looking at me. Making sure I say it right. So Evan is the guy who's been a great help in this project. So yeah, this card is one card, but it has thousands of processing cores working together in parallel. And so there are a few relevant advantages over CPUs. The first is that matrix operations are orders of magnitude faster. And that's great given the way that we coded the algorithm. The second is that you can do many, many small matrix multiplications at the same time, just because there are thousands of cores on just one card. And then imagine what happens if you use more than one card. So this is just an example. I computed the ionization potentials of these transition metal atoms. And so this is the wall time in node hours. So going from 8 CPUs to 8 GPUs, we get a factor of about 200. And then using correlated sampling on top of that gets us another factor of 32. So to study how this speed up behaves as a function of system size, we created this toy system. So we have a chain of hydrogen atoms. And then we just, to make the system bigger, we add another hydrogen atom. And then we plot the log of the propagation time as a function of the size of the chain. And so this is not even that big, 250 basis functions. So this black curve is the CPU. And again, this is an algorithm of comparable sophistication. It's just on the CPU. And then if we use double precision on the GPU, that's this. Single precision is this. And this is definitely more than 2 orders of magnitude speed up. Okay, so the talk has been, the goal, the things that we want to study are the things that are strongly correlated. And so we actually, we coded something explicitly for that purpose. And if you recall, the thing that governs how good this phaseless constraint is this trial wave function. And so the state-of-the-art way, at least for small systems, is to use something called SCF. So you have a spectrum of single particle orbitals, you identify some active space, and then you enumerate all the various ways you can occupy the states in that active space. And so this wave function is a sum of a bunch of electron configurations. And there's an algorithm called Sherman-Morrison-Woodbury, which many times we have to compute inverses and overlaps and things like that for these matrices. And those are qubit scaling things. You can update them in a very fast way, which allows us to have very, very large trial wave functions. And this algorithm is very efficient. So before, going from 1 determinant to 400 would increase the cost of the simulation by about 400. But now it goes from about 25 to 50. So it doubles it now. And that's a huge advantage. So the last point about the GPU implementation is that it has almost unprecedented parallel efficiency, at least compared to the traditional methods. So what is parallel efficiency? If I have one computer and it takes 10 minutes, this calculation. If I have 10 computers and it's a perfectly parallel algorithm, it should take 1 minute, right? 10 divided by 10. So that's not possible in things like DFT and called clustering, because it starts off with some problem, and you have to solve that problem, and then update another step. Once you solve the first one, you can solve the second. Once you solve the second one, you can solve the third. even if you have thousands of GPUs, you still have to do it sequentially. And so that's not the case in QMC, because recall, we have a bunch of random walkers. If there's 100 random walkers and 10 machines, each machine takes 10 walkers and propagates them independently. Only very rarely we have to collect them all and do things like compare their weights. But that happens, for example, once every 30 steps. So this year, we got computer time on one of the biggest supercomputers in the world, called Summit. It's capable of 200 petaflops, and it has more than 27,000 GPUs. So the first thing we did was we ran a parallel efficiency test. And so the result is that even with 360 GPUs, we're still at around 90%. So that allows us to do very big calculations in a short amount of time, assuming we have a lot of GPUs, which we do. All right, so let me get back to the chemistry. Right? We designed this method, and we want to see how accurate it is in computing properties of strongly correlated electrons. So, the first example is the atoms. The transitional atoms, we compute the ionization energy. So here I'm showing AFQMC without correlated sampling, AFQMC with correlated sampling, experiment, and couple cluster. And so with the same trial wave function, sometimes the original method was a little bit off, like maybe 0.1 eV. It's not huge. In fact, if we make the trial bigger, it'll converge to the right result. But with the same active space, if we use correlated sampling, it fixed that one. And then in all of these, we're within 1 kcal, or 0.04 EV from the experiment. So here, a couple cluster does quite well. But in the next topic, it's quite easy to break it. So instead of one atom, we take 2 atoms and compute the bond formation energy, or dissociation energy. So here's just an example for manganese-containing systems. I've plotted this multi-reference version of couple cluster in yellow, and there's 2 ways of doing QMC. Like, the big calculation is the same for both of them, but then there's something technical, which is in order to compare with experiments, if you're describing the wave function with only a few basis functions, you have to get an answer and then make sure that answer stays the same as you increase the number of basis functions. So that reaching this, it's called the complete basis set limit. That's a pretty minor correction, and so you can use other methods to estimate that. And here we use MP2 and couple cluster, 2 single reference methods. So compared to experiment, this again is the difference of the calculation of the experiment. They all do pretty good, but there are some large error bars, and it's one reason why such a study is useful. So we learned something. We found something interesting, which is that correlated sampling seems to improve the accuracy, not just the efficiency. And in one case, we looked closer. So we plotted the energy difference here at early times. And correlated sampling does allow you to measure at early times. And so this dotted line is a nearly exact method, IFCI QMC. And so we converge right onto that. And that's reflected in the measurement from correlated sampling. But if you run the normal, like without correlated sampling, for really long times, it does converge to this purple line here, which is a little bit less accurate. Okay, so here are the nickel systems and the copper systems. And I just want to point out some of these systems, they must be strongly multi-referenced. Because something like nickel hydride, even the multi-reference couple cluster, I mean, some parts of it are single reference. And that has errors of larger than 10 kcal per micron. And I'm pretty sure the issue is the inability to capture the multi-reference character, because when we use single reference methods to get this should be small basis set correction, it affects it a lot. And so we have to do pure QMC all the way to the basis set limit. But if we do that, we get experiment, in many cases where we actually thought the experiment was wrong after results like this. And then sort of the inverse happened, which was something that was very exciting. So Ben and I, we computed all these results, and then an experimental paper came out by Morse. They reported error bars that are too small to see, like they reported experimental measurements. The uncertainties were so small. But in every case, we compared to our predictions, and it fell right in line. So that was, we're actually predicting things. That was exciting. All right, so what I didn't show in those plots are what most people usually use, which are DFT and CCSDT. And so these errors are just very large compared to the QMC ones. And so here's a summary. We compared 10 DFT functionals and various couple cluster multi-reference variant. There's a lot of stuff here. The key takeaways are, at least for these transition metal diatomics, DFT seems to be just entirely unreliable. Couple cluster produces a significant improvement, as shown in the mean average error, but it still exhibits large max errors of more than 10 kcal per mole. And our QMC looks very promising with an MA of about 1.4 and a max error of 3. All right, so switching gears a little bit to the other regime of strong correlation, which is the singlet biradicals. So we just want to see how the QMC does. So here's a test set of 13 small molecules and atoms, but in all of them, the singlet state is very strongly correlated, as you can see by the DFT results, and even the couple cluster results. So we did QMC with 2 different trial wave functions. We just brute forced it with a big CAS-SCF trial wave function, and we also used a single determinant in the trial wave function, which is with unrestricted orbitals, and that we call AFQMC. This is a benefit because one can generate unrestricted single determinants very, very easily for big systems. And it's size extensive, so you can compute like reaction energies in a consistent way. And CAS-SCF, we can do it for small systems, but it does scale exponentially. So, but it's very encouraging that they produce pretty much equivalent accuracy for these pretty difficult systems. W2X is a composite method, which claims to, it's from the group of Trular, which claims to approximate couple cluster in the CDS limit. Okay, so, but remember, the target applications are these organic photocatalysts. And so we want to do something a little bit bigger, a little bit more similar to that, but still is strongly correlated. So we took these 3 isomers of benzene. So that's benzene, but you pluck out some hydrogens. There's the ortho version, where there's the 2 lone electrons are there, meta, where they're a little bit further, and para, when they're on opposite sides. So we compare our 2 ways of doing QMC with all these state-of-the-art methods. So we have not only ground state DFT, we have RPA methods, we have spin flip CI, there's another CI, oh, I didn't define it. Anyways, we have TDDFT, and we have these other methods which scale, I think, with the 7th or 8th power, so they're just not feasible for big systems. But we get very good at it. All right, so remember back to that intro slide about upconversion. The annihilator, again, it fuses 2 triplets to produce this high energy emission. So we found 2 known annihilators, and we computed the single triplet gap. And somehow there were reported experimental numbers, and so we compared against these. So DFT doesn't do great, but we do. We basically get experiment within these error bars, which are premises. Okay, so then in collaboration with Tom Rose and his student Ben, we thought that this thing upconverts. What else might upconvert? And the bigger question is, what does it take for something up? Like, it still seems like there's a lot of insights, there's a lot of details that we don't fully understand. So we just substituted CN or Ben with these various groups. So the first thing I did was compute the triplet energies. And so I compared the QMC with the couple cluster, and they get pretty similar results. And I don't actually expect these to be very strongly correlated, so that's not surprising. But DFT is 0.2, 0.3 EVs off. At least off what we think is right. But recall, why are we doing this? We want to compare twice the triplet energy with the singlet energy. And so right now, I'm trying to get S1 within QMC. That's like near the top of my to-do list. But in the meantime, I found a very interesting paper where they use these long-range corrected TD-DFT functionals, and they benchmarked it on the polyacenes. So this, ethylene, anthocene, tetracene, they're rings, and you keep adding them. So when you have 2 rings and 7 rings, they computed S1, and there are experiments for this. And the MAEs for these 2 functionals are 0.08 and 0.05 EV, which I think is pretty good. And so here we show in red and blue the singlet energy, this S1. And then we plot twice the triple energy in gray. And so I guess one thing I'll just point out is that experimentally, this compound as the annihilator did not do upconversion with an osmium sensitizer. And I think we now know why. Because there seems to be, according to this functional, S1 is higher than twice the triple energy. According to this one, it's just barely there. It's sort of within error bars. So I think this kind of calculation can be very useful in the development of new upconverters. All right, so as I said, I'm working now to compute S1 within QMC. There's also, so recall the third area of strong correlation was bond break. And I didn't really, at least bond stretching, I didn't really show results on that. And so we have some preliminary results. I went to a conference last year and met this chemist, Joe Francisco. He's an atmospheric chemist, and they were interested in the sort of early stages of how ozone actually activates. And so to me it was an opportunity because we could test out computing van der Waals energies and also barrier heights because we've never done that before. And so I'm comparing QMC with coupled cluster. And so for the van der Waals binding energy, they're basically agreed. Here's coupled cluster, here's QMC. And the error bars are about 1 kcal on these numbers. But then, interestingly, for the barrier heights, there are some significant differences here. So 4.7 to 1.5. And given the data that I showed you today, I trust the QMC a bit more, especially because at a transition state, you have a stretched bond, so that's going to strongly correlate with regime. So I'd rather trust the multi-reference method than the single reference. So anyways, that was sort of interesting. Also, at the same time, we're trying to go beyond. So we did atoms, we did diatomics, and now we're in a good position to do things like tetrahedral, square planar, and even octahedral complexes. And so we have a lot of data, but I just want to show a few. So this is with a single determinant, very cheap trial wave function. So these are, I think, either square planar or octahedral things. So Ben was running this calculation. So this is the difference from our calculated result and the experimental leading association. So here's the value and here's the error bars. And so this is very promising, even with one determinant as a trial. So what we want to do is ask the question, like, I still think that one big unknown question is what property of the trial wave function is required to produce good QMC answers. And so we're using these systems, which do have experiments, and these are real systems that people care about to answer that question. So we're going to try different trial wave functions. We're going to, different types of ligands, and try to learn things. So I guess my main project that I want to accomplish before I leave is to utilize compact electron pair specific virtual spaces called pair natural orbitals. So these are sort of revitalized by Frank Nies in Germany. But yeah, they've shown that for other methods like coupled cluster or this MP2, they can, using this virtual space instead of a general one. So for each pair of electrons, you have a set of virtuals that it can get excited to, and that the pair can get excited to. But if this pair is like far from this pair, for example, you don't have to do that. So you can save a lot of things in terms of memory, and it's reduced the scaling of many other electronic structure methods. And so we expect the same, and we've in fact written out an algorithm to do this, and we're coding it now. So yeah, one way to get to larger systems is to use this approximation, and then we can treat them fully quantum mechanically. And we expect to do things as large as metalloporphyrins, which were some of those sensitizers, but also very important in biology, and PDI dimers. We want to study certain things called a triplet pair state. And you need pretty big systems in two of them. So there's another way to scale up, which is to use a method that's much cheaper, that can already scale to thousands of electrons. So we're using the fact that QMC now we believe is a robust method that can produce benchmark quality results, especially for these simpler molecules. Like here, most of them are organics. So together with a list of experiments, which we found from a database, we're supplementing that with QMC calculations to have a test set of about 250 molecules. And this model, we're trying to parameterize a model which can correct DFT. And so there's around 50 parameters in that model, which may seem like a lot, but compared to a force field, which is the state-of-the-art way to do macroscopic biological simulations, among others, those have 10,000 parameters. So yeah, this is sort of a test, proof of concept in some sense. And so having trained this model on these molecules, we came up with 17 blind molecules, not easy ones. We have radicals, biradicals, even a guanine base in there. And so this model then reduced the error from B3 lit, which is the most popular DFT function, from about 0.26 to 0.1. And so we plan to scale this up to have a set of many thousands, and we can use things like machine learning to hopefully get even better results. Okay, so just to summarize the points that I made today, correlated sampling with the GPU acceleration typically yields speedups of around 2 orders of magnitude or more. For small to moderate system sizes, we have very high parallel efficiency, which I think is unique among traditional quantum chemical methods. finally, this method is systematically improvable. And as I've shown, it's quite accurate for a number of strongly correlated cases. So yeah, I already talked about this question, this big open question. Another future direction or project is more practical. It's just parameterizing the classical force field to encode the quantum behaviors. But a force field not for organics or drug-like molecules, but for a metal. And so you can parameterize interactions with drug-like molecules. And it shouldn't take more than potential energy curves for an octahedral metal complex and stretching in one way. And we're already doing that now. So I think this is feasible to do soon. And this would be very impactful. And finally, we can use the same theory using a certain basis actually developed by Tim and Garnet to treat extended systems. And by that I mean materials. So for example, we could compute the band gap of semiconductors, or even probe the ground state of, for example, cuprate superconductors. All right, so I guess, yeah. One of the reasons I like science, I think, is because I like people. And it's something I really enjoy, to like sit with someone and look together at some scientific problem and just dream up ideas or debug or code together. Yeah, that's been extremely fun. And there are a lot of people I should thank. I think at the top of the list are my two advisors, Rich and Dave. So this is Rich and this is Dave. They've really given me tremendous freedom and also tremendous guidance in developing as a scientist. And also, I think through their role model, I really learned what are the traits of good scientists. And so I just learned a lot watching them interact at conferences and with students. So yeah, and so I have two advisors, but I also pretty much have three. So Shee he's now at Flatiron, but I met him when he was a professor in Virginia. And so he sort of first wrote down this phaseless constraint. And so I would visit him a lot, and he would be very generous in sharing his knowledge with me. And also many of his students, like this is a postdoc of Shee's, a former postdoc, Mario, and a grad student, Hal. And in the early stages, and even now, they've been very helpful, personally and also scientifically, in learning more about this community. I guess Rule's not here, he's got a small head back there. I should thank him because he introduced me to the field of optical upconversion. Also, we've had many great lunches and espressos. And so I think he's a great scientist, and I learned a lot from him. I recently had this was a side project, which I didn't even talk about, but I think collaborating with experimentalists has been extremely important in my development. Because, as I showed, quantum chemists see the world much different. But there's a lot to be learned from the way that experimentalists who actually deal with the chemicals, get to know them. And so I've been working with Zach, among others, like Andrew, Kuhn. And so we've just had many fruitful discussions. And so yeah, here in this corner, it's sort of the QMC team. Like when I was in my second year of grad school, I was sort of laboring away by myself, obviously with my advisors, but now we have a team. Like Evan, he's been of tremendous help. We've gone on many adventures, squashing bugs left and right, like pretty late into the night. And so yeah, I'm very grateful for him. Ben Roostein, he's a postdoc in Versus Group. And yeah, I think we've only known each other for about a year, but he's very, very practical, if you know. And I tend to be somewhat idealistic. And so he's always grounding me back into reality and also making me happy and all that stuff. And Jack is the first year who I've been teaching QMC. And just, I'm teaching him, but he's also teaching me. So that's been great. So, I don't know if you guys know, in my previous life, I was a ballet dancer. And so I didn't really invite my advisors to many of these shows because I thought they would think they need to work more. But this video can't be looked at.
Find something on YouTube.
No. It's up to them.
It looked like it was.
That's there, but I can't look.
Maybe get out a presentation about
You just have to do it live.
Anyways, if anyone wants to see it, I'll show you. That's kind of sucks. But anyways, I'll do this quickly. But I've had a great time here over the past few years. These are some close fifth years. Summer volleyball days, baseball games. A few of my really good friends from Princeton. One of my dance partners, Shoshana. And this is one friend who I respect immensely. Joe, he's not here today. And also here's the QMC, early quantum chemistry PhD. You'll jump over me, you can't see. Yeah, I guess earlier this year I choreographed my first ballet, so I created a ballet. And that was a very meaningful experience for me. Having Ian and I and many other people like Liz, Pearl, we've gone on pretty epic bike rides. And so that's been really fun. Recently we won the IM championships for volleyball. Shout out to our team name was Bunsen Burners. So yeah, Jack, Garrett, Natalie, Christine, and Patrick over there. Yeah, and finally, I'd like to thank my love Mariana, who's I think watching remotely, my brother, who's been there through it all, and we've doing crazy stuff too, and my parents, who've been of tremendous support and encouragement for my whole life. All right, with that, thank you. But we could treat that with something like classical mechanics, like molecular mechanics. But in the active site where the strong correlation actually happens, we're pretty close. Like if we wanted to, we could throw the OAC into a big computer and probably get some answer right now. And once we implement this orbital localization thing, that's even more feasible. But we don't want to do that yet because I prefer a stepwise thing. We want to make sure we get one metal complex right because there's experiments to compare with. Then we want 2 metals, because then it's like interacting 4 metals. So if you just compute something and give an answer, you might get a big paper, but who knows if it's right. And there's other problems like solvation energies, which we plan to actually do. If we can create a classical force field for the metals, then we can compute free energies of solvation in a rigorous way. So there's all these things that I think I would prefer to be careful about and approach systematically to make sure we actually have accuracy. So every day we're learning about the physics constraints. Yeah.
You mentioned you're starting to work on the S1 excited single states.
Yeah.
What's the feasibility of, is it even perhaps possible to get an S2 state or S3 state, just some higher value single state?
I think so, yeah. Shee has a paper where they produce, I think, a band structure. So you can get a bunch of excited states. I think it's based on something where you, in the trial wave function, you orthogonal. You make sure your walkers are orthogonal to, if you want the second excited state, you enforce the constraint that it has to be orthogonal to the ground state and the second excited state, or the first excited state. And then you'll get the next lowest value, which will be the same. So that stuff's possible. I think my friend Mario is working on an EOM method for AFKs. And so that'll more easily get a spectrum.
Any other questions?
Yeah.
You mentioned H2 model, the hydrogen H2 model, and then you also mentioned the bonding and the anti-bonding.
Yeah.
It's possible to know how many. For maths, I only know in the H2 molecule there are only bonding. There's no. I don't know whether they have the anti-bonding. But I just wonder, is it possible to use the QMC to know how many percent of the bonding and how many percent of the antibonding?
Well, I guess, so first of all, for H2, there's always, if you have one atomic orbital for each H, there's always going to be a bonding and antibonding orbital. But then that's actually a single part of the picture. So reality is a many-body thing. And so these orbitals that you occupy in a singular W, that's a model. So I don't know if this is the most important thing to